Hi guys, we're doing very exciting stuff at the moment. We just proved the bare category theorem, which is still displayed here on the slide. Countable intersection of dense open subsets in a complete metric space is always going to be dense. I discussed already one application, which is still written here in yellow and green. This is about the interval 0, 1 of real numbers being uncountable. After proving bare category theorem, now we're going to prove or derive much more important stuff than 0, 1 being uncountable, although that's also important. And in order to derive this, we need the following corollary to the bare category theorem, which is written down there. In a complete metric space, if you have a family of closed sets whose union is all of it, all of X, then at least some of the CNs should have a non-empty interior, which kind of intuitively makes sense. How to prove? Well, I already said whenever you apply bare category theorem and you go from open to closed, you use complements. So let's do it. Proof. If all Cn, so it's proof by contradiction, have non-empty interior, set, well, complement A sub n, so the closed ones again, X minus Cn. Now remember, the Cn's are closed, so the complement's going to be open. And then each An is open. And since all of them have empty interior, that's the important thing, not non-empty interior. I want to show that at least one of them has non-empty interior, so let's assume that all of them have empty interior. Okay, so looking at the complement, there's a complement of open sets, so they are of closed sets, so they're definitely going to be open, and they're going to be dense. And dense in X, since, well, the interior, Cn interior is empty, right? That's fine. All right. So, but then what have you created? You have an intersection of, you have a countable intersection of open dense sets in a complete metric space. So that means this thing has to be dense. Thus is dense by the bare category theorem. And hence, in particular, and so, in particular, not empty. Okay. Yeah, but thus, if you look at the union of the Cn's, well, by De Morgan's rules, this is the complement of the intersection. Well, that intersection is non-empty, so X minus that intersection, well, will not gonna be all of X, right? Is not equal to everything of X, and that contradicts the assumption of the current proposition or corollary. Okay, is not all of X. This shows, so a contradiction. This shows that some Cn has a non-empty interior. Okay, that is the corollary. Good, very nice. So now we are ready to prove the first big theorem. I mean, to me, it's one of the biggest in this introductory module on functional analysis, which is the principle of uniform boundedness. This is likely the result that we're going to use most often as we continue this class. So PUB, principle of uniform boundedness. It goes as follows. Let F, curly F, be a subset of bounded linear transformations from one Banach space call it x with a norm indexed by x to another one, call it y, and the norm indexed by y. Now suppose that that family is pointwise bounded. What does that mean? Well, it asks for each x the following supremum tx, y, and the supremum is taken here over members in the family of bounded linear transformations. And the pointwise bound means that for each given point small x, there exists a constant c which depends on x, such that, not epsilon, such that this guy is bounded by this constant which depends on x, right? All right, that is the pointwise boundedness. Okay. Now the magnificent truth is then that this family is actually uniformly bounded. Then f is uniformly bounded, meaning you can optimize over x here in that first line with the supremum, and when you optimize over x, you generate the operator norm. Tf less than infinity. Okay, that is the principle of uniform boundedness. All right, so let's read it again. A subset of bounded linear transformations between Banach spaces. Then if that family or subset is pointwise bounded, meaning you have pointwise bounds, so for each x you can find this constant which depends on x, and of course this constant, when x goes to infinity, it might explode, right? But that's pointwise boundedness. But actually the constant does not explode, because that's the theorem, that's the statement of the theorem, right? Because it's uniformly bounded, so you can optimize over all x, and when you optimize these guys over x, you of course get the operator norm. That's why you have this. Okay, good. So this is a principle of uniform boundedness. This is a magnificent result and extremely important. A few comments before we prove it. There are other words for this guy in the literature, but that's not such an important comment. Besides PUB, principle of uniform boundedness, it also goes under the name Banach-Steinhaus theorem, and we will use this thing foremost for linear functionals. So going back to the previous section, so we will apply this thing mostly for bounded linear transformations between a Banach space and the underlying scalar field, aka linear functionals. Okay. Now the comment that I want to make is that you cannot dispose of completeness. So this is not because sort of we weren't able up to this point to come up with a better proof. No, completeness is essential. So here's an example. For if, yeah, let's take an incomplete normed linear space. So let's take continuous functions with the one norm. So that's not a Banach space. We proved this a while ago. That thing, the continuous functions on 0, 1, is only a Banach space when you equip it with the infinity norm. Okay. And now family of bounded linear transformations, actually functionals here, so that family will be indexed by small n, so Tn. Those are bounded linear transformations given by, well, essentially the antiderivative. So Tn of f takes f of t, dt, integrates it, not all the way from 0 to 1, but from 0 to 1 over n, and multiplies it out front with n, right? So that's going to be a scalar, right? And since integration is linear, and you can easily prove that the right-hand side is bounded by some constant, and that's a bounded linear transformation from x to the scalar field, so a continuous linear function. Okay. Note, by the way, by the substitution rule for integrals, you can absorb the n outside into the integrand, but then it will show up in the argument of f, all right, given by this. Then, for each f in x, because these are continuous functions, and continuous functions on compact intervals like 0, 1, they are bounded, right? So there exists a constant c, which depends, of course, on the continuous function that you're working with, so that you have tnf. Well, you have absolute value here outside, you go inside with the triangle inequality, and then you bound this guy here in absolute value by your constant c. And then you have to multiply it by the length of the integration path, which is 1, right? So you have this for all n in n, right? And see here the right-hand side, that constant c does not depend on n, right? So that's why, in short, this family f indexed by n is pointwise bounded, right? Remember the statement of principle of uniform boundedness. The first thing about pointwise boundedness takes a supremum over all members in the family, and what comes out is independent of the member of the family. And that's precisely what happens here. It only depends on the point on which you evaluate your linear function, and that is f, because this constant surely will depend on f. All right? So, but now, well, if you believe that principle of uniform boundedness also holds in non-complete spaces, now then this would state that this has to be uniformly bounded, right, that family, but that's not the case. Here's an example. Look at g sub nx, so which is 2 times 1 over n minus x, so this is linear function from x 0, 1 over n, and then at x equals 1 over n it is already 0, and then to the right of it you just set it identically equal to 0. So this is certainly a continuous function, and now you can convince yourselves that that guy, I'll just have to compute the area of this this triangle there, is 1. And if you stick it in up there in the linear functional, let me write it like this. So the operator norm is at least as big as, well, that functional evaluated on Gn, but that actually you can evaluate explicitly is equal to n, and that of course as n goes to infinity becomes unbounded, right? So you don't have uniform boundedness here, okay? All right, good. So that is the comment that I want to make. Now let's prove it. And this will use bare category theory. There are other proofs of principle of uniform boundedness, but I will go through bare category. So let's define C sub n, x in x. These are all points such that, well, these guys, supremum taking over all members in this family of bounded linear transformations, do not exceed some small n, with n being a natural number. Okay, now we want to apply this corollary that I called it, yeah, it's a corollary of bare category. So I have to convince myself that this is now a closed set and the union is the whole space, right? So let's first convince ourselves that this is closed. So if you have a sequence m in the Cn with xm going to some x as m tends to infinity. Now how do I show that the limit is also in there? Then for any t in f, well, t of x in y norm is, okay, so t limit m goes to infinity xm y. Now since there is, we're working with bounded linear transformations, they are continuous, I can pull out that limit here, and then even better, because the norm is continuous, I can pull out the limit all the way here. And then you have limit m goes to infinity txm of y. Yeah, but for this one, by construction, remember this is a sequence in Cn, this here is at most small n, right? So, and then small n doesn't depend on m, so this is at most small n, right? At most small n. Yeah, but then this means in turn that x lies in Cn, by definition of Cn, right? So x in Cn. Id est, Cn is closed. All right, now we have to convince ourselves that the union of all those Cn's is the whole space, but this is easy because that's how they are constructed. Given that f is pointwise bounded, the union of all the Cn's is going to be everything, right? That's precisely what pointwise boundedness means. For every x, that supremum taken over all members in the family of bounded linear transformation is finite. And here I bound it by small n, so if I exhaust all n's from 1 up to infinity, I'm going to capture every element in the space x. Okay. Hence, with this in place now, by the corollary to the bare category theorem, for some, remember the corollary was saying that some of those Cn's will have a non-empty interior. So for some n naught, there exists an n naught such that the interior of C naught is non-empty. Okay, what does this mean? Well, you can squeeze in an open ball in it, right? That this meaning there exist x naught, delta, and n naught, so that b delta x naught is in Cn naught. Okay, but this means what? Just recall the definition of the C sub n's. This means if you are at most distance delta away from your x naught and you pick a member of your family, then the operator norm, not the operator norm, the norm in y of the image of x cannot exceed the n sub naught. That's precisely how the C sub n's were constructed, right? It was actually saying the supremum over all t's. Okay. Now letting y be the difference, x minus x naught, we see, okay, now comes the usual shifting around, exploiting the linearity, right? Because this we haven't done so far yet. Or we use the linearity in the sense of continuity, right? So that we used there. So we have y of x less than delta and t in f. Well, then you use the triangle inequality. Ty of y is then gonna be less than or equal to n naught, and then here you're gonna have tx naught, right? This is just by triangle inequality, and then you can optimize these guys here over all members in the family, right? And that's gonna be, of course, a finite quantity. Let's move this line a little bit to the left. Right, so you have initially here t of x minus x naught. You use the triangle inequality, you write it as tx plus tx naught, both in norm, and then you bring the thing to the other side. This is actually the triangle inequality at the lower end. And then you have the tx naught here in y norm, and then you can estimate it from above by the supremum taken over all members in your family. Yeah, but this is going to be finite by assumption because of pointwise boundedness, and of course you add here a finite number to it, so you're going to have something finite. Okay, good. Replacing now, replacing y by y1 plus epsilon. We would like to have here a closed ball. Right now this is in the open ball. of radius delta, but we would like to have a closed ball. That's why this little surgery. And taking epsilon to 0, we see that we can change y less than delta to y less than or equal to delta. Alternatively, you could just go to delta over 2. But okay, let's do it like this. Thus, what have we achieved? If t is in f, we have, well, this one here on the right is bounded by c, a universal constant which is independent of the element y and of the member t in the family, so you can optimize over it. So you can look at the operator norm, supremum, okay, let's do it. Yx equal 1, ty of y, and then what do I have here? Well, you have to divide by the radius as usual, 1 over delta, and then supremum. And that's why I said either you can do this epsilon surgery or you can go to delta over 2, and you also have a closed thing there, ty, and this is going to be finite, right? Less than or equal to c over delta, which is finite. Okay, and that's precisely what we wanted to show. This proves the uniform boundedness of the family. Okay, and you're done. All right, so this is remarkable. It's remarkable. It uses the corollary to the Baire category theorem crucially at this point up here, right? So having the pointwise boundedness, you define those sets C sub n. You convince yourselves by continuity of the bounded linear transformations that it's closed, and the pointwise boundedness yields that the union of all those things is the whole space. Okay, and then you are in Baire category world. You conclude you have non-empty interior, and then you're essentially done. You just have to translate this non-empty, having a non-empty interior into the boundedness of the operator norm. Okay, very nice. So this is the first important consequence. And now it will happen like dominoes. Now comes immediately the next one. So theorem, we will just state it. This is a bit of a longer proof. I will make some comments and then we will prove it in the next video. So this is the open mapping theorem. So open map, okay, let's state it first, then I will talk. So let T be bounded linear transformation be a bounded linear transformation between two Banach spaces, again, x and y. If that thing is surjective, so if the range of T is equal to y, then it is actually an open map. Then T is open. What does that mean? That is, it maps open sets in X to open sets in Y. So if A in X is open in X, then the image of it, so T of A, which are just all points Tx, where X is in A, is open in Y. Okay, that's the statement of the open mapping theorem. Now, open mapping theorems in general analysis are very popular. Maybe some of you are taking or have taken a class in complex analysis, and there's also an open mapping theorem in complex analysis, so stating that certain non-constant functions with special properties, the analytic functions, they're also open maps. They map open sets to open sets. There you actually don't need the surjectivity at all, right? And usually these open things, the open mapping theorems, they're very remarkable because in the ordinary world, So here we're working with bounded linear things between Banach spaces and surjective objects. But if you drop one of those constraints, then usually everything falls apart. And at least when one discusses the open mapping theorem and complex analysis, one usually gives this example, right? So you can look at trigonometric functions, sine or cosine also works. And that thing, though very nice, you know, infinitely many derivatives, real analytic and whatnot, it is not an open map. Of course, it's clearly not linear, so there something is wrong, because it maps the real line, which is open. It maps, well, to something non-open, which is the closed interval, right? By the way, this map here is surjective, right? So that works too. So here what really fails is the linearity, right? Good. The open mapping theorem we will prove in the next video. Again, it relies on bare category theorem on that one corollary. And then once we have open mapping, then immediately comes the next big thing. It's the inverse mapping theorem, and then the closed graph theorem, which is the fourth big theorem in this section. And then I think we're almost done with this section. Okay, but all in all, very, very important results right now. They are important because they are used frequently in the material that is still going to be discussed from now on. All right, I look forward to seeing you again in the next video.